Good afternoon, everyone. I hope you can see us and you can hear us. My name is Jose Pizarro, and I am the East Coast manager for Fermentis. On the screen on your top, and I'm going to be your moderator this afternoon. I am not going to give this presentation. Below my image, you have Anne Flesh. She's our West Coast manager for Fermentis, and she will be doing this presentation. And on the top right of the screen, you have Kevin Lane. He's our technical sales support manager with over 10 years of experience in the brewing industry, and he will be our backup speaker if there is a kind of glitch with the Anne's connection. So as you can see on your screen, we have been putting 2 polls. Now the second poll is running. And the idea was to know if you knew the strains we were going to talk about. So a few housekeeping information. The way to interact with us is through the chat. I think people that have been on this webinar cycle before know how it works. But during Anne's presentation, if you have any question, please drop the question in the chat. I will be taking notes, and we will answer by chat, or Anne will take the question, or maybe we will go to the question at the end of the presentation. So, Anne, the floor is yours, and thank you.
All right, I'm just going to present the result to you, just so you have an idea of how you compare with other people around you. So I'm just gonna take note of this, and then I can start. All right, let me move to the presentation, and we'll talk about maybe the results of this polls later. All right, here we go. Today, we are going to talk once again about the 3 dimensions of fermentation. We started this cycle of webinars last week, and my colleague Kevin, that you just saw, presented to you the first part of this 3-part dimension. And today, we're going to talk about the second dimension, which is the influence of the fermentation parameters. All right, so what is today's agenda? So 3 big chapters. The first one is going to be kind of a reminder of this concept of the 3 dimension of the fermentation. What are we talking about? Really just trying to explain a little bit, remind you what was presented last week, just as a quick reminder to start off with the same basis, and then start to discuss what happens if we start changing the parameters of fermentation. And then chapter 2 and chapter 3 are going to be 2 case studies on specific yeast of our portfolio. The first one is going to be a lager strain that is one of our most popular lager strains, Sapphire W3470. And I asked you earlier in the poll if you had used that strain, and the idea was to see, okay, we're talking about this strain. Let's see who used it. So let's say for 15 people answered the poll, and you said that 60% you used that strain before. And then we have the case of Saf Ale BE256. So in that case, it's in a ale strain from our portfolio, a Belgian strain. And in that case, you said at 67% you haven't used it. So we're going to talk about different things. We're going to talk about each study, what protocol we did, and then what type of fermentation parameter we changed. And then we looked at 3 different axes. How did that affect the fermentation performances? How did that affect the production of the volatile compounds, looking at the analysis of this volatile compound? And the third aspect, of course, the most important, is how it affected the sensory analysis of the beers. All right, the 3 dimension of fermentation. For those of you that were here last week, Kevin introduced the same slides. I'm sorry for the repeat here. The idea is to know, what do we know about fermentation, and what did we used to know about fermentation? I think fermentation used to be kind of like a black box. And this is what represented here, with everything that you would do before fermentation. So wort preparation, where we had a good idea of the consequence of your action on the wort preparation: malting, mashing, lautering, boiling, wort clarification, and so on. And the post-fermentation, that was also very clear: processing, aging, lagering, filtration, carbonation, packaging, and so on. But fermentation remained kind of a black box on how the parameters and what you would change would affect the beer. And so the idea is that at Fermentis, we're trying to kind of make this black box a little bit more gray. And this takes me to my next slide, and kind of represent of this black box as a 3D world, a 3-dimension world with that are driven by the yeast, of course. So the first axis, and I'm gonna use my pointer here, is going to be what we call dimension 1, and that's going to be the yeast characteristics, the intrinsic yeast characteristics that are, based from the genetic of the yeast, that are going to give different flavors, aromas, also different fermentation qualities, flocculation, sedimentation, of course, attenuation. So in the same wort, yeast are going to behave differently. So that's dimension 1. Then the second dimension is the one we're going to focus on today, is the fermentation parameters, the things you have power on when you ferment your wort. So what are we talking about? Of course, there are many things that you can do. We're going to focus here. We can talk about the temperature, the pitching rate, the initial gravity. It could also be, the tank you're using, different pressures on the yeast, and amount of nitrogen. We can't focus on everything. So today, we are going to focus on things that you have a lot of control over, which is temperature, gravity, initial gravity, and pinching rate. And the third dimension is something that Kevin will talk about next week, and it's a very interesting topic, is the interaction of the yeast with raw material in your wort. So it could be malt, it could be hops. We've done a lot of work so far on interaction with our yeast with hops, but we also started doing more and more work with interaction on malt. So stay tuned for next week for the third dimension here. All right, this is also kind of a reminder of what we presented last week. It's what we call the baseline. So the baseline is a representation of the flavors and aromas of all our brewing strain in the same condition. So nothing else is varying there but the yeast, the strain that we used. So what is the idea? Is that we used a very neutral wort, so 15 Plato wort, 100% spring, 2 rows, with a bitterness of 25 EBU, only brought by iso-alpha extract in order to bring bitterness, but no flavor. We didn't want to have any interaction with the raw ingredients there. The pitching rate that was chosen for all the strain was 50 grams per hectoliter. So for those of you who are familiar with our product and our dosage recommendation, 50 grams per hectoliter is kind of in the range of what we could recommend for an ale strain, but we tend to recommend higher pitching rate for our lager strains. So it's pretty conservative for the lager strains. And then the same way, the temperature that was chosen, so 23 Celsius. It's more in line with ale fermentation temperature than most recommendation for lager strains. But the idea was really to have the same condition, and then we have atmospheric pressure, so really simple conditions. And then you have the representation of that is based on sensory analysis. So here you have 3 different axes. You have here the fruitiness, here the spiciness, and here more of the neutrality. And we place all our yeast strain on this diagram with the ale strain in red, the lager strain in yellow, and then you have in a special purple here what we call fermentation solutions that are a blend of yeast and enzymes. And at this point, we have HA18. And so what you can see is obviously that, first of all, we have a very diverse portfolio when it comes to the intrinsic characteristic of the yeast. And the lager strains can go pretty far up in the fruitiness, but also in the spiciness here with WBU6, B134, our saison strain, T58. Those of you who are familiar, you know that these strains are puff positive, so can bring spiciness to your beer. And then at the opposite, you have some strains, some very widely used strains that are really more neutral and really put the emphasis on the other raw materials. So in the ale portfolio, you're going to have USO5, and in the lager portfolio, for example, Saph Lager W3470. So that's what we call the first dimension. That's the baseline. Now, the question that we're going to ask today is, what happens if we change the conditions? So the idea was to take specific strain individually and start playing with fermentation parameters. Of course, these are usually really quite extensive studies, so we can't do everything at once and present everything. It would be pretty overwhelming. So what we do is we started with 2 strains, and we chose 2 strains that were quite different in both in their genetics, their origin, their aromatic profile. And we started with these 2 strains. So these are Saph Lager W3470, our most popular lager strain in our portfolio. And you can see that 3470, like I said, is a quite neutral strain. And then at the other side, we're gonna, at the end of the presentation, we'll talk about Saph LB256, a Belgium strain, very fruity, very aromatic, so quite different. And we're gonna start moving the fermentation parameters. All right, so like I said, very different strain. This is just another representation. You have on the left our this lager strain we're going to start with, so Saccharomyces pastorianus of German origin. So it's a lager strain from the Froberg family, bottom fermenting. And at the opposite, we're going to talk about BE256, top fermenting of Belgium origin, Saccharomyces cerevisiae. All right, so let's start with the study on Saph Lager W3470. So like I said in introduction, I always start with the protocol, and then I'll present fermentation results, volatile results, sensory analysis, and try to finish with what you as brewer can take home as a message if or when you want to use this strain. All right, so Saph Lager W3470. Like we said, really widely used strain, lager strain in the world, Weihenstephan strain. The lagers that it produces tend to be soft, clean, really free of esters with a focus on the raw material. The beers might have some slight sulfur notes derived from the yeast. But what we expect from this yeast is really to give to beer a neutral fermentative profile. So what is the protocol of this study? So all of these trials were pilot trials that were done in 50 liters pilot trials. And we did 14 different conditions where we started playing with the initial gravity. So we went in a scenario of 12 Plato, 16 Plato, 20 Plato. Then fermentation temperature, 12 Celsius. Here I put the conversion in Fahrenheit, 16 Celsius and 20 Celsius. So 20 and even 16 when it comes to fermentation of lager can already be considered medium to high temperature. And then for the pitching rate, we had not 3, but 4 scenarios with from 25, 50, 100, and 200 grams per hectoliter. The recommendation that we have for our lager strain is our 80 to 120 grams per hectoliter. So you can see that 25 and even 50 would be considered under pitching to severely under pitching. And at the opposite, with regular temperatures, which we have here, 200 grams per hectoliter could be considered over pitching. And we had, once again, a very standard recipe, wort 100% malt, Pils malt, 28 EBU, and we did a direct pitching of the yeast, which means no rehydration, according to our study, our new easy-to-use certification on our yeast. And once again, we looked at 3 different things: how these 14 scenarios affected fermentation performance, the volatile profile, and the sensory analysis. All right, so just a small focus on sensorial analysis. We have a professionally trained panel at Fermentis that we use extensively for this type of study. So for this type of analysis, it is blind test. So all the samples are random, coded randomly. We have an average of at least 22 trained taster per sample. For the pilot trial, and then each of the time 3 repetition of this tasting. So the idea is to have the best result possible, to have statistical relevant information. And here you have kind of a picture of what it looks like. You see the people tasting there, really blind samples. And here at the top, you can see the type of question that the panel is asked. So here, typically, it's just for one criteria. We ask them the fruital characteristics, so how fruity the beer is. And what they have to do is they have a bar here from not detected to high levels, and they have to put the cursor somewhere in this bar. And then this is then transformed into a number. All right, so that was the protocol, and now we are moving to the fermentation performances. All right, so this is an overview of the 14 scenarios, and at the top of this slide, you have all the conditions from C1 to C14, and then P stands for pilot. And you can see all the different parameters. So the density for each scenario, the temperature, and the pitching rate. And here you have the result of some fermentation, of a very important fermentation characteristic, which is the duration of the fermentation in hours, and also the ethanol. And here we represent the fermentation kinetics. So it's a little bit hard to read when you look at all the scenarios at once, but we can make a few conclusions just looking at this quickly. Is first of all, there is a really wide variation in fermentation duration from 4 days up to 19 days, in the 14 conditions tested. Even these scenarios at the end might not have properly finished. So very, very wide variation. You can also see that you have 3 groups, the one starting at 20, 16, 12, Plato. Clearly, just generally speaking, the higher densities tend to take more time to ferment, which makes sense. You have more sugar, the yeast has more work to do. But it's not the full answers, because you can also see that you have some long fermentation that are associated with low pitching rate. So for example, you have C13 here. C13 you have at 25 grams per hectoliter. But you also have long fermentation associated with low fermentation temperature. And for example, C1, you start at 16 Plato, 12 Celsius. And you are also, you're very, very slow there too. So we're going to take a look really in detail for each initial gravity. It's going to help us read this graph a little bit better. All right, here we go. So here we are, just the scenarios for the 12th Plato. And so we have 4 different scenarios. We highlighted them for you here with the right color. So what can we see? What are the main conclusions here? If you compare C4 and C10, you can see that really they're both fermented at 20 Celsius degrees. There is a minor impact of the pitching rate there. At this temperature, we went from 50 gram to 100 gram per hectoliter, and C4 and C10, have very, very similar fermentation curves. So at high temperature, pitching rate, raising the pitching rate doesn't impact too much. If you look at C11, so C11 is going to be 12 Plato, 12 Celsius, and 25 gram per hectoliter of pitching rate. So everything being very low has the longest fermentation time from all the scenarios. And then if you look at C4 and C12, you can see that low pitching rate, like we are here at 50 gram per hectoliter, can be compensated with the temperature. So here we move from 16 to 20 Celsius between C4 and C12, and you can see that there is an improvement, a clear improvement in fermentation time. All right, here is a focus at 16 Plato, and you're going to see that there are a lot of very similar conclusions here. For example, if you look at C5 and C8, once again, you can see that at the blue and the green scenarios here, you can see that once again, at 20 Celsius, moving from 50 to 100 gram per hectoliter does not affect too much the fermentation. If you look at C1, you can clearly say it's the slowest fermentation here. You can see that the low temperature, 12 degrees, and has an effect on the fermentation clearly with a 50 gram per hectoliter, so quite low pitching rate. And then if you compare C1 and C5, so here C1 and C5, you can see that once again, it's an example of how temperature can compensate a low pitching rate. So here, both scenarios are at 50 gram per hectoliter, this one, and the C5 in blue. But we moved from 12 to 20 Celsius, so quite a dramatic change in kinetics. All right. Oops. And here we are at 20 Plato. So the last slide really dedicated on looking at the kinetics specifically. Here we have more scenarios. So 1, 2, 3, 4, 5 scenarios. What can we see here? In this case, for example, if you compare C2 and so C2 in green and C3 in purple, you can see that actually a very high pitching rate. So here we move from 100 to 200 gram per hectoliter. Help favors the fermentation speed at 16 Celsius. So in the previous slides, we were at 20, and we saw that increasing the pitching rate didn't help. Here, you can see that at lower temperature, improving the pitching rate can help. And if you look at the 3 scenarios, C2, C13, and C14, you can see that these are different variation of low temperature and low pitching rate, a different combination of temperature and pitching rate that kind of illustrate that there is an higher influence of temperature versus pitching rate. So for example, C13, you have, it's in orange here, you have 16 Celsius and very, very low under pitching at 25 gram per hectoliter, but you have faster than a scenario where you are at 12 Celsius for fermentation, but 100 gram per hectoliter of pitching rate. So it seems like there is a higher influence of the temperature rather than a pitching rate. All right, so we looked at all these scenarios now. looking at all this data and compiling all this data, we can create what we call a correlation matrix or Pearson matrix. And trying to read this, what you have to do, it's pretty simple. We have a table and we have the different parameters of the fermentation and the different results, duration, ethanol, and you have a number in this table where the parameters meet these parameters, and each number is going to be between 1 and -1. And the closer you are to 1, the more these two parameters are positively correlated. The closer you are to -1, the more these two parameters are negatively correlated, and the closer you're to 0, one way or another, the less these two parameters are correlated when it comes to fermentation. So an example of a very good correlation is, for example, ethanol and density, how much ethanol you get with changing density. And in a very obvious way, it's a very good correlation of 0.98, so very close to 1, between ethanol and density, just to give you an example. So when we look at the duration of the fermentation, which is what we were looking at, you can see that really the best correlation is going to be the temperature, and it's going to be a negative correlation, which means the higher the temperature, the lower the fermentation time. You do have a correlation with density too, but it's a little bit not as good of a correlation. So 0.57 here. And you see that there is very limited correlation with pitching rate. So 0.0026, very, very bad correlation number. All right, so what are the main conclusions of this first part? The conclusion is the higher the density, the higher the fermentation part, but mainly the higher the temperature of the fermentation, the lower the fermentation time. And that's something that you can apply very easily at your brewery if you want to save time on fermentation, moving tank faster, and so on. That's something that's a very strong tool on fermentation. So now let's see how these affect the volatile compound and the sensory analysis. So firstly, the volatiles results. All right, so here we are looking at the production of higher alcohol by the yeast, and we have two graphs. The first one is the production of different alcohols here. You have the main higher alcohol produced by the yeast, and you have the different scenarios from C1 to C14, and you have the production of these molecules in ppm. Which is interesting to know, but most people don't have in mind what is a high or low concentration of these molecules to be perceived. So what we do is we very often express this data under the unit of flavor unit. So the flavor unit is pretty much the concentration in ppm divided by the threshold of perception of an average human being for this compound. So it's done on individual compounds, and it uses an average human. And so what it tells you is that here you have really the limit of 1. 1 flavor unit means you are at the threshold of perception for this molecule. So what's interesting to see here is for the higher alcohol, and in all these extreme conditions that we've seen, slightly really high under pitching, low fermentation temperature, high fermentation temperature, very, very limited amount of higher alcohol produced. You're most of the time under 1 threshold of perception for each component, and the ones that are higher are under 1.5. So main conclusion for the higher alcohol, the main higher alcohol produced is isoamyl alcohol, which is a very the most common higher alcohol produced by yeast. It correlates positively with the density. So if we look at the same correlation table, you see that the correlation is 0.8, so quite good. And also with the pitching rate, but with very, very limited amount produced. So it correlates with some fermentation parameters, but you stay really under, for most components, under the flavor unit of 1, and for the others under 1.5. So very hard to they should be very hard to perceive. And then if we look at the same type of graph here, we look at the esters and the 4VG. So same thing, you have the first gram expressed in ppm of these esters and 4VG produced, and then we transform this in the flavor unit. And you can see that once again, most of the esters and 4VGs are really under the threshold, the limit of 1 flavor unit. You can see that yes, some esters are produced more than others, but really still under the threshold of perception. And so, most conclusion, you can see this is everything that's above 1 here. You can see that there are very limited amount of components that go above 1. The ones that are the most produced for the esters are ethyl hexanoate, isoamyl acetate, but they have a minor impact on flavors. And here we put this table where really you see how extreme the conditions are. So here we are at C3. You see C3, there is nothing over 1 for esters, and you are at 20 density, 16 Celsius of temperature, and 200 grams per hectoliter of pitching rate. So everything, all the parameters being quite high or very high. And then you have C11. So C11 here, where you have slightly one molecule above 1, and you are at 12 Plato, 12 Celsius, and 25 grams per hectoliter. So 2 scenarios very extreme from each other with results of the same apparent neutrality. All right, and here we look once again at the correlations between the parameter, and we are looking here for the scenarios that are at 100 grams per hectoliter of pitching rate. And if we look at this correlation table here and we focus on this part here, these are the production of all these aromatic molecules. You can see that they are mainly correlated with the density more than the temperature. As just the phenylethyl alcohol tends to be more correlated to the temperatures than the density. And once again, the duration of the fermentation is very well correlated with the temperature. Here, it's a very good correlation at this pitching rate, which is the recommended pitching rate for this strain. And so the conclusion is really that increasing the temperature, you can really accelerate the fermentation without affecting the aromas and flavor of the beer, at least looking at the volatile analysis. So now we looked at the analysis. Let's see how this was perceived by the panel. All right, so here you have a table that that reminds you of the different scenarios, and at the top here you have kind of what we call a spider graph of the results given by the panel with the different scenarios for each criteria: fruitiness, bodiness, acidity, bitter, sweet, off notes, sulfur, and so on. And the first thing that we can say is the scenarios are judged as very uniform. You don't see a lot of discrepancy. All the scenarios are really on top of each other. So this is kind of a hard way of looking at the data. You don't see very well the details. So this is another way of looking at it that might be more visual. Same thing, you have the same question asked to the panel about these beers. And what we can see here, you have the criteria that have the little stars are the ones that are judged as significantly different by the panel in terms of statistical analysis. So the 2 that were just judged statistically different are the sweetness and the off notes, and then the ones that have more of a tendency to be different as the alcohol and the warmth. And you can see that it excluded the off notes. The 3 other criteria are criteria that are very linked to the density. So probably we're going to see that this is going to be linked to more the initial density of the beer more than other parameters. And we'll take focus on the off notes in following slides. This is yet another way of looking at the same data where we only took one criteria, so the fruitiness, how floral the beer were, how sulfury, and then you look at all the different scenarios, and it's pretty incredible to see how flat these results are with such extreme scenarios once again. All right, I said we were going just to focus on the off notes. So we ran extra analysis just to identify specifically what off notes we were talking about. And we asked more specific questions to the panel. And you can see that there are really two scenarios. So it's going to be C1 in brown. So 16 density, 12 temperature, and 50 gram per hectoliter pitching rate, and C11, mainly C11 has a peak of diacetyl, 12 density, 12 temperature, and 25 pitching rate. So what they have in common is they have low temperature and low to medium low pitching rate. And what you have to remember is that the temperature here stayed constant. So if we say 12 Celsius, that means that we really didn't raise the temperature at the end. So it's not really surprising to see for very low temperature this peak of diacetyl that haven't been reduced. And also the fact that if you have a low pitching rate, most likely you have a low yeast population. So less capacity of this yeast population to reduce the diacetyl. So all of this makes sense, and these off notes can be explained with the protocol. So the main conclusion, both on the volatiles and the sensory, are the higher the density, the higher the volatile production. It is correlated, but with very minor sensory impact, both judged by the panel and by the flavor units. So you do have an impact, but you can sense it. And also the lower the fermentation temperature, first of all, the higher the risk of slow fermentation. We've seen that in the first part, but also the higher the risk of slow notes. So pretty much positive impact of raising the temperature, less risk on fermentation of notes. So I wanted to just give you a take-home message for this study. Really, what this study has shown us that was, I think, really us in the Fermentis team, we were very amazed how neutral this strain really stayed in all conditions. It's very robust and stable over many different conditions, and it can really ensure a faster fermentation at higher temperature without affecting the beer. And that's something that we've had many brewers, client brewers starting to do, and being very happy on how neutral the beer stayed, but also on how it didn't affect the profile of their lager and stayed a really clean lager. All right, so that was for W3470, and it seems that most of you are familiar with this strain. Now we're moving to Sapphire BE256 case study. A bit less of you are familiar with this strain, but even better, it's an occasion to hear about it. And it's we're going to go through the same different stages: protocol, fermentation, performances, volatile, and sensory analysis. All right, Sapphire BE256. So an ale strain that is judged as very fruity, so with some estery, some also floral characteristics. Also in some beer show well some hoppiness and maltiness styles, and we tend to recommend it for really strong ale styles, Belgium ales, Belgium strong ales, British strong ales, American strong ales. So beers that tends to be associated with high ABV, where it really it seems to show its best. Also, I think I said it, a strain of Belgium origin. So you can see in our portfolios strains that some strains there Belgium starts with BE for Belgium. All right, the protocol. The protocol is very similar from the W3470 study, but the scenarios are a little bit different. So same thing, we are still in pilot trials, and we start changing 3 parameters: the initial gravity, temperature, pitching rate. For the initial gravity, we are the same threshold, 12 Plato, 16 Plato, 20 Plato. And then for the temperature, we have 12, 16, 20. And here we added 24 Celsius because we know that with this strain, people like to ferment at higher temperature. So one more scenario. And for the pitching rate, we have one less scenario than for the previous study. So we have 25 grams per hectoliter, 50, and 100. And for our ale yeast, we recommend a little bit of a lower pitching rate than lager yeast. So here our recommendation is 50 to 80. So you can see that 25 can be judged as under pitching and 100 as over pitching, with 50 being a medium. And same recipe, very standard neutral recipe, wort 100% malt, 28 EBU, direct inoculation. And we're going to go through the same process. Okay, fermentation performances. Here you don't have the legend for all the scenarios, but if you look at all the conditions, once again, you can see just like for the previous study, you have a wide variation in fermentation time from 15 to 14 days, with a tendency of the higher gravity to take longer to ferment, but of course, this is not the whole picture. So we're going to do the same exercise. We're going to look at each initial gravity. So here we are at 12 Plato, and we have 4 different scenarios. And what really shows here is scenario C11. So C11 is 12 Plato, 12 Celsius, 25 grams per hectoliter. So everything being very low. And you can see that the low pitching rate and temperature really slows down the fermentation compared to all the other scenarios. And something else that it shows that it also lowers the degree of fermentation. And this is illustrated here on this graph, where you have the concentration of the different sugars after fermentation. So you have here the 4 scenarios, and then you have a bar for each type of sugar: glucose, maltose, so DP2, and then maltotriose, DP3, and then DP4, DP5, DP6, DP7, and so on. So what we're going to look at here is really the DP3, the maltotriose. You can see that for this very low pitching rate, low fermentation temperature, there is much more maltotriose left at the end of fermentation. So definitely an effect there of these conditions, both pitching rate and temperature. All right, here we are looking at 16 Plato. So we have one more scenario, and same thing here. You can compare C1 and C5. So C1 is going to be at 12 Celsius and 50 grams per hectoliter, and then C5 in blue is going to be 20 Celsius with the same pitching rate. And you can clearly see here the effect of the drastic effect of temperature moving from 12 to 20 or from 20 to 12. That really slows the fermentation. And once again, it also lowers the degree of fermentation. And if you look at C1 versus C5 here, you can clearly say the really high amount of maltotriose left here at the end of fermentation. So here you have the single effect of the temperature on maltotriose. All right, and last group of scenarios, 20 Plato. So here a little bit more discrepancies in the results, but if we really focus on C13 and C14, you can, once again, you have these two scenarios where you have, one is C13 here is going to be 16 Celsius, 25 gram per hectoliter. So very under pitching. And here in orange, C14, you're going to have 12 Celsius and 100 gram per hectoliter of pitching. So really pitching more. You can see that under pitching or low temperature, both scenarios really slow down the degree of fermentation. And if you look at the maltodextrose in both situations, both under pitching and low temperature, you have a lot of maltodextrose. It's really the effect of both. And you can see also that C14 is slightly faster than C14. So globally overpitching can compensate low temperature is also a conclusion. All right, so now you know the drill. After that, we can look at the correlation. And now you all understand the correlation table. So I'm just going to highlight the most important facts. Here, really, we can see there is a negative correlation again. When temperature increases, fermentation decreases, and with a pretty good correlation of -0.7. So here again, fermentation temperature is a big driver of fermentation time. All right, we had a focus on another fermentation parameter, diacetyl and correlation. And here you can see the different scenario and the amount of diacetyl at the end of fermentation. And you can see with the threshold of perception here highlighted in the pink box. And you can see these two scenarios here being way above or above this threshold of perception. And that's going to be C11 again and C1. And you can see that in both cases, C1, you are at 12 Celsius, and C11 also at 12 Celsius, with also very low to, average to low pitching rate. And what we see is that there is a really a good negative correlation between temperature and diacetyl production. So when the temperature of the fermentation increases, the diacetyl concentration decreases. And also, if you look, for example, at C14, you can see that you can compensate. You can compensate the low temperature with a higher pitching rate. So C14, where are you here? You are at low temperature, but by adding more yeast, that is going to be able to reduce this diacetyl more. You're gonna be able to compensate this low temperature. All right. If we look at all the fermentation correlation data and all, these are the main conclusions. So here you have the temperature, the initial gravity, and the pitching rate, and I try to highlight the important data to look at. If you look at the temperature, really, the most important is that the highest the temperature, the more you decrease your fermentation time, and the more you decrease your diacetyl level. When it comes to density, really, the highest the density, the more residual sugar and extract you're going to have, and you're going to see that all these criteria that are really linked to sugar have a good correlation with the initial density. And then pitching rate, the best correlation that the pitching rate has is with the real degree of fermentation. So the higher the pitching rate, the highest the real degree of fermentation is. But when you look at the real degree of fermentation rate, its balance between temperature and pitching rate seems to have the same effect. And I think we've seen that in the trials. All right, let's look at the second level of analysis for these studies of volatiles. So here you have a reminder of the different scenarios again, and you have at the top the total alcohol, the higher alcohol produced, and the esters produced at the bottom. And in that case, we didn't separate the higher alcohol by nature or the esters. It's a sum of all of them, and it's expressed in ppm. But you can see that there is a large variation here, and if you look at all these scenarios that are high in total alcohol, what they have in common is that they all have a good combination of high temperature, high pitching rate, high Plato all together. And at the opposite, the C11, it's low temperature, low pitching rate, low Plato. And the esters, all the scenarios that have really high amount tend to all have high initial gravity. So the gravity seems to be a big driver here. And at the opposite, C9 is at the lowest gravity, so 12 Plato. So if we look at the volatiles now expressed in flavor units, so here you have all the volatiles, you have all the higher alcohol esters, but also 4-VG and diacetyl. And once again, one flavor unit being the threshold of perception of these aromas. You can see that it's a drastically different picture from W3470. You have these, for isoamyl acetate, you have a peak at 6 flavor units for some scenarios, but really high production for most scenarios. You have the 3-methylbutanol, which is the also another name for the isoamyl alcohol that is related in the metabolism to the isoamyl acetate, also peak. These two molecules are really linked to the production of strong banana aroma in beer. And then you have also here high concentration of ethyl acetate. Ethyl acetate is an ester that is linked to fruity, but also associated with some solvent characteristics, and some small scenarios that are above 1 for 4-VG, but limited. It is a puff negative strain, but maybe for very high density, because we know it's linked to the raw material. But that's a global picture. So if we look now, this is the same graph, but expressed just with the molecules that are above 1 flavor unit. The conclusion are 4-VG, just globally a low presence, which is what we expected from this yeast. Then you have the ethyl acetate and a 3-methylbutanol that are a very important marker for this strain for most scenarios. For all scenarios, but some more than others. Then you have ethyl butanoate. We didn't talk about it in the previous slide. It's an ester linked to more tropical fruits, sometimes pineapple. And it's only above 1 for 1 scenario that is high density, low pitching rate, cis13. And then mainly the main characteristic is really going to be the isoamyl acetate. And we can really say that it's the banana yeast. That's how we can a nickname we can give it. And then ethyl hexanoate, I didn't talk about it in the previous slide. It's another esters. It's a marker and more for some scenarios than other. It's linked to some more anise, apple, pear fruit, this type of aromas. All right, so we looked at the production of the volatiles. Now let's see how this is correlated with some of the fermentation parameters. So here in this table, you have the correlation table, and in purple, we highlighted the molecules that are above 1 flavor unit for the isoamyl acetate, way above for the ethyl hexanoate, only for some scenarios. And here, I try to highlight for each component what are the best correlation. And you can see for the 3 esters, and mainly isoamyl acetate, that's the most of concern, the best correlation is really the initial gravity, the Plato. So 0.9, 0.9, 0.64, really good correlation between the amount of sugar that you have to ferment and the amount of esters that you produce. For The higher alcohol, you can see that there is a good correlation with pitching rate, Plato, and temperature, which is pretty much what we saw when we analyzed, the first graph of the volatile compounds. So summary on the second axis for B256, the most important volatile compounds for B256 are for the ester isoamyl acetate mainly, also ethyl acetate and ethyl hexanoate, and they all positively correlate with gravity. And when it comes to higher alcohol, the main one is going to be the 3-methyl-butanol, and it positively correlates to all parameter studies. And so once again, you can see the dominance of the banana on this slide. So interesting results. Let's see how it correlates with the sensorial results. Here we have the spider graph from the tasting panel results, and you have the different scenarios, the different questions asked to the panel, and you can see that the graph looks very different from W3470. You have way more variation between the scenarios. It's a different picture. You can also see we highlighted with the little asterisks here the significant result, the significant statistically significant differences. So the main criteria where you see statistical difference between the scenario are going to be the warmth of the beer, the body of the beer, the sweetness of the beer, and the alcohol content of the beer, perception, of the beer. These are significant, and the ones that are highly significant are going to be the fruitiness. Look at this difference, really very high difference between the scenario, and also the sulfur perception. So these are very significant, fruitiness and sulfur. And we have the correlation table just for the sensorial analysis. So here, once again, you have the variable. I highlighted the ones that are significantly important between the scenario, and the ones that are very significantly important. You can see the fruitiness highly linked to the initial gravity, which is in line with what we saw with the esters. So esters were highly correlated to the initial density. And for the sulfur note, you can see that there is a decent negative correlation also with the initial gravity. So it seems that the lower the gravity, the more chance you have to have sulfur notes. And then for the other criteria that are more really linked to pretty obviously to high gravity, alcohol perception, sweetness, warmth, body of the beer, it's confirmed by the correlation that these all have really good correlation with the initial gravity. So this seems like a complex slide, but it's actually pretty easy to understand. This is the result, an overview of the analysis of variance, also called ANOVA, that we're gonna use in the following slides, where really what we do here is you have the different scenario and you have the different questions, analysis asked to the panel on the beers. And here you can see again which ones are significantly different. So fruitiness, remember, yes. Floral, we didn't see a significant difference between the scenarios. Alcohol, yes. Sulfur, yes, but phenolic, no. So, and then what you can see, you have the mean average for each scenario for all the tasters. And then each scenario for each criteria is going to have a combination of letters. And here we have a focus just on the fruitiness here. All the scenario, you can see that all the scenarios that has the highest in fruitiness have a letter A, and then it goes to B, to C, to D, to E. And the way to read this is a scenario that has A is going to be significantly different from a scenario that has B, but a scenario that has A and B is not going to be significant different from a B. It has to be significant different from a C and a D, and so on. So this is this type of analysis, and we'll use this in in the next slides. So questions are based on all this analysis. What are the most fruity and floral conditions? So here I highlighted the fruity ones. And you can see that it's C2, C3, C6, C7, C13. All of these have a letter A or AB. And you can see that all of those are really, really linked to high density, 20 Plato, 20 Plato, 20 Plato, 20 Plato, 16 Plato. So really linked to high gravity. If we look at the floral here, the highest floral perception, it's going to be C7, and it seems to be linked to underpitching. So 25 grams per hectoliter. All right, another way to look at this data with a different angle. Once again, here you have the means of the different production of the different scenarios for the character fruitiness, and you can see the ones that are above 5 in this red box. So C1, C13, C2. C6, C7, the ones we were talking about. And when we look at the correlation, we can really see that for fruitiness, really good correlation with, once again, the initial density, 0.8, really good correlation. Floral, so it's interesting to look at it, but remember, in terms of results, we couldn't see significant result between the scenarios, which is very different from the fruitiness that was extreme significant difference, but it's still interesting to see with what it is correlated. So it seemed to be correlated to the pitching rate. Look at the previous slide, and this can be confirmed. You can see that the best correlation that we can find for floral characteristics is a negative correlation with pitching rates. So really a lower pitching rate brings you more floral characteristic in your beer. And then when it comes to sulfur, here I highlighted the scenarios that have the highest mean, that are in the A group or A and B. And the main scenario is going to be C4, C8, C9, and C12. And you can see that in all these cases, you are at low, so 12, 12, 12, or 16 medium density. So really sulfur seems to be associated with lower density, but also the two scenarios that have the highest amount are not only low to medium low density, but really high, over pitching yeast. So it seems like a combination of low density, so low amount of sugar to perform with bringing too much yeast seems to be problematic conditions for this strain to produce sulfur. So let's see how it correlates. Well, we kind of have a confirmation here. There is a decent negative correlation between the sulfur and the initial gravity, and also a decent correlation with the pitching rate. So it seems that both of them combined could be a reason why you could have sulfur in your beer. So what are the main conclusions on this volatile and sensory part? The density has the biggest impact. We've seen it both in the volatile and the sensory. The higher the density, the more mainly esters you're going to produce, but also fusel alcohol and residual sugar, along with sweetness, perception, and body. Also, the higher the density, the lower the sulfur perception. So what I forgot to say about this sulfur is that we don't know if there is more sulfur produced, or it's just that you don't have these at lower gravity, or if you just don't have these esters to cover it. The analysis doesn't say. Another conclusion is the impact of the temperature. The higher the temperature, once again, we see the fermentation time, the lower the fermentation time. So it's a good tool to play on your fermentation, but also the lower the diacetyl level, and the highest the production of higher alcohol, but also esters. And finally, the pitching rate. mostly impact negatively on the floral perception, and also is correlated, the higher the pitching rate, the more real degree of fermentation you would have, and we've seen the impact on the maltotriose mainly. And so what is the take-home message that we can have with B256? It was our perception, but it's been confirmed that it's really a strain that provides very fruity flavor over many different fermentation conditions, but especially for really high density, high fermentation temperature beers, really strong beers. And it's really ideal to brew strong and flavorful, rich, for example, Belgian ales. So that was it for this part of the study. I wanted just to remind you, so I told you about the webinar we had last week about the first dimension, the baseline. That was this one. Today we talked about the second dimension of fermentation. And next week we'll have the third dimension, which is, like I said, the interaction of the raw material with Kevin, our technical sales support for the Americas. So should be pretty interesting. And then the last webinar that we have is going to be in 2 weeks, and it's going to be what we call the last frontier on hard seltzers and kind of tips and tricks on how to ferment hard seltzers. And with this, I think I'm done with my part. Maybe I invite my colleagues to join me and maybe help with answering questions that you might have.
Yeah, thank you, Anne, for the presentation. I think we can put the chat on the screen. Please let us know if you have questions on any of the slides that Anne was presenting or about dry yeast in general. I think Kevin, myself, and Anne will be happy to answer those questions. Let's see who is going to be the first person to drop a question in the chat.
I was so clear that there is no question.
That's really the best presentations, when there are no questions.
Well, I don't know. Maybe it would be nice to hear in the chat, has anyone who is here with us today tried to, for example, ferment at higher temperature for with Sapphire W3470? Oh, Jeremy's writing. So now it's us asking questions. You're welcome, Jeremy. Oh, you are planning on fermenting. Well, you know, please send us an email, and we're looking forward to hear back. But we're not too worried about the fact that you'll be happy with the results.
Yeah, I will say that it is interesting now that we are presenting all these, releasing actually all this data on the strains, that you can see that some of the strains, you can really steer the flavor production based on fermentation parameters, and other strains like 3470, like whatever you do, they are going to produce the same beer, which it's really interesting for production, time-wise, and also pitching rate-wise. Like you can save time and also money by buying less yeast, for example.
Yes, for sure. And I think if you are interested, you will come up with more studies. So these were the two first strains that we selected, and we'll move on with a couple of strains per year in order to really bring not too much information at once to the market. But so you should hear about new studies soon. Yes, actually, I answer your question at the time you typed it. Yes, and I believe we already communicated about, we have the latest study we communicated on at HomeBrewCon, correct, Jose?
Yeah.
On B134.
Yeah.
So the next one will be B134, and maybe we'll have a webinar just specifically for that strain in the future.
Exactly, yes. We communicated recently about B134. And so, Kevin, there is a good question here. Brian is asking, what is the highest temperature 3470 will still ferment? Above 20 C, which is 68 Fahrenheit. So what are your thoughts about, like, how high can you go?
I think that depends on a couple of things. With this question, how high is the highest temperature that it'll still ferment? That's a pretty open question, not talking really about the flavor profile. So if the question is how high can you ferment and still have a consistent flavor profile, I would say 20 degrees is probably as far as you will want to go. We didn't test above that, so we can't say for sure that if you go to 25 or 30 degrees C that it will still react the same. So from our study, we can only say 20. How high is the highest temperature that it'll still ferment? That's much higher than that. It's just that we can't guarantee flavor profile or consistency in that.
Yeah, I think to add on what you are commenting, Kevin, with the pandemic, we had a lot of people using our strains to produce alcohol for hand sanitizer. And in this scenario, the idea was to produce alcohol fast without caring about the flavors profile. And I think we had a couple of customers not using 3470, but using spirit strains that we have, and they push up to, I think, 95, 100 Fahrenheit. And the strains were still fermenting very well. Like, of course, that was for sure full of higher alcohols and fusels, but the target was not to drink that, just to produce alcohol. So I think we can get quite high.
Yeah, most yeast strains should be able to tolerate above 100 degrees Fahrenheit. It's just that, again, your flavor profile isn't going to be what you would expect. Mm-hmm. In terms of being the same in that neutral characteristic. So I would say 20 degrees C, 68, 70 degrees Fahrenheit, somewhere in there. It's really fast and you'll still have that neutral flavor profile. Beyond that, we don't know, so we can't say for sure that you could go to a higher temperature and still expect the same results. There's another question. Curious, how long did these two studies take? And I can talk about that a little bit. So whenever our R&D department starts one of these studies, it takes quite a significant amount of time. Really, what Anne showed and showed very well today is just a summary of these studies that we did. As you can imagine, some of the fermentations, you saw the time of the fermentations were taking a month or longer to finish. And that's just the fermentation part. Then the beer has to be processed. It has to go through the analytical lab and all of the measurements taken. And then has to go through taste panel. All of that has to be scheduled. We have to reach a certain number of tasters to qualify the information as being a complete tasting. And then comes a really complicated part where we have to do all the analysis on the data points. And that can take a long time as well. So, it's a simple question, how long did it take for the two studies? But really the answer is complex. And really the number of fermentations, the number of measurements, the number of times it was through our taste panel, all of that produces a very long timeline for these studies to happen. I can tell you that from being part of the technical team in Fermentis, usually we're targeting, about a half of a year between these studies, maybe up to 9 months. It depends. Right now with COVID, I have no idea how long it will take for the coming studies to come out, because it means that there's going to be less people to taste beer, less people in the building, less people on the campus to go to the taste panel. So I think that the coming studies, which I know one of the strains that's coming up that I'm interested to see, but I'm positive. I'm thinking positively about it, that the results should be communicated to us by the end of the year. But But again, with COVID, I'm not sure, how long that delays this study and then the coming studies after that.
Thank you, Kevin. Jeremy Baker has a question that I've seen before. So he wants to know if we have plans to study different fermentation. To study variations in the fermentation temperature through the trial, because as Anne mentioned, all these trials are done from start to finish with the same temperature.
Do you want me to answer that?
Of course.
I guess I can answer. I do not believe that there is a plan to do that, because really the point of this study is to show how one temperature is going to affect your beer. So for sure, I understand your question. You want to know, with applicable in what you want to do in your brewery, how it would affect. But if we start doing that and, you change temperature at a specific time, we're going to start having so many variables that it's going to be very hard to draw some statistical conclusions. So the idea is really to have one temperature, maintain it, and really see how these affect the flavors. That being said, we know that for some cases, for lager, the chances of you raising the temperature, and of course, but it wasn't the point of the study. But yes, it's hopefully in the future, when we are done with the plans that we have, maybe we could start having scenarios where it's more where we vary these type of things, but it's not in the plan yet.
Yes, thank you.
Correct.
For clarifying that. And
I've asked this question myself, so I know.
Yeah. I think we are all curious by nature, and the more we know, the more we want to know. So in this kind of studies, actually is unlimited. I think me and Anne are more on the sales team, and Kevin is on the technical team. And when we have meetings together, we let them know all the ideas and trials that we want them to run. And of course, as any company, there is a budget for R&D, and we have to prioritize what we are studying first and then later. And also, like Kevin will assess if the question is pertinent or not. I think all the questions are good, but for sure, some need to be answered before others. And I think personally that if we had answers for any question you have, then the craft of the beer will be gone, because we will be able to nail everything we want to do. And right now, the beauty is that some people, like with the same ingredients, can make amazing beers that other people cannot replicate it. So for sure, there is a lot of science, but there still be some alchemy in all this.
And I think, just to talk a little bit more on that, when you look at how complex this study is as it is, where we're studying, 3 temperatures or 4 temperatures or 3 pitch rates or 3 different or 4 different gravities, whatever number of each component we're looking at, it's already complex. And then take into consideration what I'll talk about next week, which is studies focusing on interacting with different different raw materials. And that, again, just as Jose said, is an infinite possibility of different things we could test, because you look at it, there's 80 or 100 and some different hop varieties that these can interact with in different ways, and different malts and the preparation of malts and the amount of different water around the world as a base for all of the beer. And we could test 1 billion different recipes and have different conclusions about that. So just consider how much we're already looking at, and it would be great, like Jose said, if we could figure out exactly with everything, if you had a temperature increase over time, if you did sequential yeast additions, how that would affect the fermentation. But it's, number one, it's simply impossible to do because there's so many different variations you could do. And number two, we're already looking at a lot of material between these studies about the controlling the environmental conditions, or what we'll talk about next week, the interaction with raw materials and how complex that gets very quickly.
Yeah, I think that's a nice talk. Another dimension, what's going to happen with the different kind of biotransformation yeast can do with raw materials. It's really interesting. Let us know. So I think we can take maybe 2 or 3 or more questions. There is
There
one.
is a question on the presentation, slide 56. I'm going to move back to the presentation mode so I can go back to slide 56, Jose.
Yeah, go ahead. Go ahead.
So if you can monitor the, okay, 56. Someone had a question on this slide. So I don't know if seeing the slide helps you remember the question, maybe. I don't know if in the meantime you want to read another question.
Sure. I think, Kevin, this can be interesting for you as you are a lot in touch with R&D. Clément Chevalier is asking, do we sometimes ask untrained regular beer drinkers to try or test brew to see if they can sense any difference between the different fermentation parameter beers?
I saw that question while I was scrolling through. I have another one that I'd like to talk about, or I'd like you to talk about, Jose, actually next. But no, we don't ask untrained tasters to taste. The reason being is we're looking for really, we're looking for if a taster that's familiar with beer and flavors in beer can identify the different characters in the beer. And what I mean by that is, as a former taster for a company in the brewing industry, it takes a long time to train on flavors and to be able to identify flavors at threshold or close to threshold. And if you were to ask somebody off the street, most likely they won't be able to tell that much of a difference. But that's not what we were looking for in the study. We were trying to see if it was a trained taster, does that correlate with the analytical numbers, first of all? And second of all, can you pick out certain characteristics in the beer? For example, and this is kind of like the general example, when I was a trained taster, I taught my wife how to taste diacetyl in beer, which most people would just say, it's not exactly perfect, but they wouldn't necessarily say, oh, that's buttery or butterscotch, if it's somebody that's not trained. So the reason that we do a trained panel is so that they can identify those things and say, this has buttery diacetyl character. Let's take a look at why that has that character. And then you go back and you can see that it's higher diacetyl level, and it's because the yeast was struggling during fermentation. So no, we've never submitted these to untrained tasters on purpose, because I don't think that we would necessarily gain too much from having somebody that wasn't trained tasting it, and really to see the correlation of tasting with the analytical numbers that come from us analyzing the beer.
Yeah, I think to add on what you mentioned, Kevin, being a professional taster is something that you have to train for on a regular basis, and actually something that you have to be controlled for. And I think the key is to know where your blind spot is. So that's why I would say in this kind of experiment, it doesn't make sense to run tasting with people that are not trained for tasting, because it's not, what we want is consistency in the feedback, and you get only that with a trained panel. So we have a question from Chris Jones, a good question. He's asking, were these trials done in closed stainless steel conical vessels? And he's wondering if we have ever done testing with different fermentation vessels, like open fermenters, Yorkshire squares, and so on.
We have not. Of course, it'd be great to do that. Maybe in the future.
Yeah.
We'll see. I mean, right now we're trying to get an idea, from the way Anne introduced it, from the baseline through changing the environmental conditions, or whatever you can change fairly easily with pitch rate, temperature, and gravity, and seeing how that affects the yeast. In terms of the different vessels, I think number one, I would be interested to see how many people are making beers in open fermenters in this chat. Usually it's not too many. Usually it's cylindrical conical. Usually, of course, there are exceptions. But, really in an open fermentation, you can't control the environment completely, or you have some airflow that's going to change if somebody walks in the room. And that will affect or could affect the fermentation. So it's not as easy to control as a closed tank.
Thank you, Kevin. Please let
there was a question.
Yeah,
Jose, there was a question earlier about oxygenation, but I don't see it anymore.
No, it wasn't a question. It was a statement.
Yeah.
Oh.
That they were recommended 2 weeks ago at our a few weeks ago about our easy our active dry yeast presentation, not to oxygenate and dry pitch, and they were amazed by the results.
Okay.
So, yeah. Excellent. Let us know if you have a couple of more questions. We will be really happy to answer them. Of course, can be strain related, dry yeast related. So please go ahead.
Ryan Rogers.
Ryan, you're here every webinar. Thank you for being good support.
I think, Kevin, that's a question for you. What can you tell us about yeast and lag phase, and actually dry yeast and lag phase?
I mean, that I've had that question a number of times in the past 6.5 years, almost 7 years now. And I don't know. So there's a couple of things that he's talking about here. One that really makes sense to me, and the others, I'm not sure if you can make like a scientific correlation between them. When you rehydrate in a brink, you're going to limit the lag phase because you're having the rehydration happen in a separate tank before you're adding the yeast to the fermentation. So you're immediately eliminating, I don't know what the time period is. I think it probably depends on the yeast just getting into solution and then being hydrated and moving forward. I'm not sure that the amount of dry yeast or oxygen at knockout would change the lag phase necessarily. Maybe it works, but I don't know that there's any scientific evidence that either of those would change lag phase, because lag phase is really it's a characteristic of the yeast strain. So last week I was talking about the intrinsic character of yeast strains. The lag phase, that period when the yeast is acclimating to the environment before it really starts growing, fermenting, is a characteristic of the strain, not of conditions that you're applying to it. So maybe you're seeing a faster start to fermentation. I don't know, maybe, I don't know why more dry yeast would change that.
Yeah. Would be nice to know what strain, for example, are we talking about US-05 here, or?
And oxygen, I don't know if you're oxygenating while you're 04.
Yeah, usually 04.
Honestly, I don't know.
Yeah, usually 04 start to ferment right away. It's a very vigorous strain. And as Anna was saying, like, we know that US-05 has a lag phase. So it's not a surprise. But 04, it's a little bit, a surprise if you are seeing a lag phase with it.
How big of a lag? Wow, up to 24 hours. That's surprising. I can't say that I've heard of that. with USO5 for sure, a 24-hour lag phase is pretty standard or pretty normal. Not standard, but can be. I would expect that from USO5.
And what's your pitching rate? Are you in the recommendation of 50 to 80 grams per hectoliter? We're asking more questions. So.
So let's take the
so that's a little bit
calculator. No, but that sounds about right, actually.
Okay.
Yeah.
Yeah.
Like a brick, each 7 barrels in that ballpark. Yeah.
No, it's 65 grams per hectoliter at the 1.5 kilo. I mean, there's a lot that can go into that, but I think 1.5 kilos per 20 barrels that's a good add rate for the yeast. That's, it's over our minimum, below the maximum. It's right in the middle, actually. So that would be the average amount that we would recommend. I don't know if that's when you're having the lag or if it was at a lower dosing rate.
I think, Kevin, in the meantime, Jeremy is asking, well, he knows that we release a dry bacteria, Lactobacillus plantarum, and he's wondering if we are planning to release a lactic acid producing yeast. So
that's what we have, in fact.
No, yeast.
Yeast, not bacteria. Yeast.
Oh, yeast. Oh,
yeast.
sorry.
Yeah, I think he's referring to what some other companies are doing with a GMO or non-Saccharomyces. Yeah.
Not that I'm aware of right now. I mean, Lesaf Group, our parent company, has a pretty strong stance on the GMO. So we won't necessarily. I mean, the way that I understand is that there's a strong stance against GMO for consumable product. But times can change.
Might be linked to the fact that we are a French owned company, and in France more than in maybe Northern America, it's a little bit more frowned upon in consumable goods. So
yeah. Going back to Jeremy's question, I think the answer is no. We don't have that yet. But maybe you guys will be interested to know that we release in the market a yeast strain to produce non-alcohol beers or low-alcohol beers. So a specific microorganism that is maltose and maltotriose negative. So I think each company has different priorities.
Yeah, JP, I think you should just keep that going forward. Honestly, I'm surprised that you had a 24-hour lag phase with SO4. Maybe if you reach out to the website, you'll get in touch with the right salesperson, depending on where you are. I don't know if anybody knows who that is, but get in touch with a salesperson and we can talk to you more specifically about your process and your wort that you're having the 24-hour lag phase with.
Perfect. Yeah, I can see Jeremy, he's aware about LAO1. Well, let us know if some of you guys want some samples about one of the products of one of the strains actually we have been talking about. Let us know and we will be happy to send you a sample to try. I think we can take one more questions and call it an afternoon before the next week presentation. And I think if there are no questions, I think that's it for today. So, well, thank you again for your presentation. Thank you, Kevin, for being today with us. And looking forward for next week webinar and the last one that I will be doing about seltzers. So quickly, Eric, no yet. We don't have yet homebrew size for LA01, but yeah, we can stay in touch. I cannot tell you. I don't know when we will make that happen, but at some point we will release it to the home market. And
maybe I'm not sure.
Yeah,
because of the beer being so high in fermentable sugars, that for commercial brewers we recommend that you pasteurize the beer. So for a home brewer to set up pasteurization would be difficult. Not to say that they couldn't do it, but there's a risk to using LA01 because all of the maltose is still available for yeast, which would be 50 to 70% of the fermentable sugars in a beer. So I don't know if we'll release that or not for home brewers. My thought is that we probably won't, just because it's a challenge to make a beer and to stabilize it as a home brewer.
Mm-hmm. Thank you, Kay, for the clarification. Yeah, jumping on something that Ryan is mentioning. So all of our strains are gluten-free. So if you use our strain with gluten-free grains, you should be good to provide to your customers some gluten-free options as well.
And there are gluten-free extracts in the market. Sorghum extract is gluten-free, but I'm not going to speak on if that makes a good beer or not.
I would say it's different, but it's a legit option to have.
Or rice. There's rice extracts.
When you haven't had a gluten-full beer in a long time, I think it tastes good.
Yeah.
Excellent. Well, thank you, everyone. Have a great afternoon. Bye.
Bye, everyone.
Bye.
See you to the next one.